Hello and welcome back. So we will continue our discussion of interesting ideas in data science. So far in this course, we've seen a lot of algorithms, especially those that deal with high dimensional data, etc. And at the core of all these algorithms was the idea of randomization or using probability as an algorithmic tool, right? So if I had to put it down, so far in this course, we have used probability as an algorithmic tool, but probability in general in machine learning goes much deeper and can be used as an analysis tool as well. So what I thought I'll do in for a couple of weeks from now on is to use probability, or is to use C ideas which use probability as an analysis tool, right? So to analyze goodness of machine learning algorithms, so to say, right? So we are going to see probability as an analysis tool, and this will take us into the idea of statistical learning theory. Which, if I have to at a high level explain what this is just understanding, when do the machine learning algorithms that we have seen in previous courses, when do they work and why do they work, right? So how can we make guaranteed statements about when some algorithms will work, and how can we use probability as a tool for this, right? So that's the basic overall picture. So for this, what we will do is, so this is I mean, statistical learning theory is a course in itself. So my goal here is not to do the entire full-fledged statistical learning theory ideas, but at least give you a solid introduction, couple of weeks of introduction, so that you know how probability can be used as a very powerful analysis tool in understanding machine learning algorithms. Right, so that's the goal for the next couple of weeks, starting today. So what do I mean by statistical learning theory? So let's put down formally what we want to do. So let's say let's look at a standard machine learning problem where you are given some data set. Let me call this data set as S. It has x1, y1 dot 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 xn, yn. So there are n samples that are available, where these data points are in some d-dimensional features. In this, I mean, in the next couple of weeks, we are not really going to worry about scale per se, but we'll go back to classical standard machine learning, right? So data points are in some d-dimensional space, and yi, the labels. Think of this as a simple binary classification algorithm. So the labels are either 0, 1 or plus 1 or minus 1, however we want to call them. So this is the data that we have, and what happens, so we pass this data to some learning algorithm. This could be any of the algorithms that you have seen. This could be, for example, logistic regression. This could be support vector machines, decision trees. No, we are kind of agnostic to the exact algorithm for most of this this part of the course. So there is some learning algorithm, and the goal of the learning algorithm is to convert my data set into a model, right? So a model is just some function. Let's call that function h. It depends, of course, on the data. So we'll put an s below. So let me write it carefully. So hs, just to indicate that h is a model or a hypothesis, h for hypothesis, and depends on s. S is the data. And what is this? This is just going to be used to make future predictions. So this is just a function from Rd to plus or minus 1. That is, h of x is just a function. The input is a new test data point, and then the output is plus 1 or minus 1, right? So if it is SVM, think of this as some classifier W that you learn, and then hs of x, right? So example hs of x could be some sign of W transpose x plus B, right? So that could be a function. So we are not fixing what this function is at this point. We are just saying there is some function that an algorithm learns. Depending on the algorithm, the function might differ. If it's SVM, it could be sign of W transpose X plus B. If it is decision tree, then HS itself is the decision tree. And then you give the input, it passes through the decision tree, various features are checked, and then finally an output is obtained, and so on. So we'll abstract all that out and say that HS is just a function that maps RD to plus or minus 1. Now, we want to understand the bigger goal, right? So the goal of all of statistical learning theory is to ask how good is HS in predicting unseen data. And that's a very tricky question to ask, right? So because we have learned HS from our data, which is S, which is just a bunch of examples with labels, and we want HS to do well on the test data, which we have not seen so far. So which means that there should be some way to relate the train and the test, because I mean, if there is no relation between what we will see in the test and what we have seen in the train via S, then no matter how good your learning algorithm is, you are going to suffer in predicting for the test data. So there should be some relationship between the train and the test, and the standard relationship that one assumes is that both the train and the test data come from a same distribution, right? So we have to make some assumptions before we answer the question, how good is HS in predicting unseen data, right? So only when we know what is the relation between train and the test data, then we can ask this question more meaningfully. Otherwise, if train and test have nothing to do with each other, this question is a vacuously, the answer is, it could be pretty much useless. But we don't want that, so we will make some assumptions, and the standard assumption that relates the train and the test is the following. So there is a distribution, and this is a distributional assumption. There is a distribution, and let's call this distribution D over, in this particular example that we have been setting, that we have been seeing, this is a distribution over RD cross plus minus 1. What does that mean? That means that that just means that, you know, there is a probability distribution that gives me the chance of seeing a particular feature and a particular label associated with it, right? So if the feature space is continuous, then this is a density function basically. The label space is of course discrete. So basically what this is saying is that, you know, if example, if my feature is, let's say D is three-dimensional data, maybe my feature is 0.1, 8, 7.3, and then labeled plus 1. Now if I ask this question, now what is the chance that, you know, I will see 0.1, 8, 7.3 with a label plus 1, then there is this distribution D which tells me that, hey, this has this particular density, right? So this is there is some density for this particular specific set of numbers to appear with the label plus 1. And this is just an example. I mean, for every such value there is some density associated with it, right? So one simple way, I mean, of course, one simple way could be, let's say here is a way to, one particular example of a distribution D could be, you know, a two-step process that tells me that completely specifies the distribution D. So let's say P is the probability of y equals plus 1, which means 1 minus P is the probability y equals minus 1, and the density of x given y equals 1, this is just a Gaussian centered at, let's say, mean 1 comma 1 with variance 1 0 0 1. I'll explain what this means in a minute. So density of yx given y equals minus 1 could be another Gaussian which is centered at minus 1 with covariance 1 0 0 1. Now this could, my D could be this, right? So what this means is that In pictures, this just means that, you know, I have a two-dimensional data in this case because the centers are just two-dimensional points. This is in R2, this is in R2. And what this is saying is that, you know, there is the center 1 comma 1, right. So, and then there are these contours around that, circular contours around that for class 1, class y equals 1, and then there is center -1, and then the circular contours that tells me about class -1, right. So, this is class y equals -1. Now, what does this tell me? This tells me that, you know, for every point, right. So, now I can, for example, pick any point, each and every point I can ask a question that, let us say here is a point. Now, maybe this point is -0.5 comma 10, that is this point, and now I can ask, hey, what is the chance that I see -0.5 comma 10 as my feature and my label is +1, right. So, now there is some chance that, you know, this distribution D gives me that label, right. So, how would I, so for example, if this is how I break it up, so then there is some chance with which my label is +1, which is P. So, this would be just P times, this is the P, and then the density which is centered at, you know, because I am asking for 1. So, this would be a Gaussian density of this Gaussian, the blue Gaussian, centered at off the point -0.510 with parameters 1, 1 and covariance matrix identity, right. So, now that would be the chance that I see -0.5 comma 10 with a label +1 in my data. So, what this means, right. So, what we are, I mean, this is just again an example, right. So, this is not the only type of D that we care about, but when I say a distribution D over RD comma plus or minus 1, what I mean is that, you know, there are these there is a probability distribution over the feature space and the label space, the joint distribution over feature and label space. This can be Gaussian, this can be anything, we do not know. So, only assumption that we are going to make is, you know, this is a fixed but unknown distribution. What does that mean? That means that all my training points are drawn IID, right. So, independently and identically distributed according to this distribution D, right. So, think of this distribution D as a black box with a button, and then I press the button, out comes an x comma y pair, x1 y1. If I press it again, I will independently generate x2 y2, press it again, independently generate x3 y3, and that is how my entire data set has been generated. That is the assumption. Now, that is not just the assumption, the extra assumption is that when I am testing, right. So, when I get a test data point, again I independently press the button and I will get a x comma y, but I do not show you the y, I just show you the x, right. So, the algorithm is just shown the x, the feature, and asked to predict what the y is, right. So, that is the connection. This distribution D is what connects my training and the test data, right. So, that's the basic assumption in statistical learning theory, that there is a distribution over, you know, over the feature and the label space.